Let's go to the next speaker. It's Mark Wiese. And by the way, I always had a problem. Is it Weiss or Wiese?
Weiss.
Weiss. I thought so when I saw you. Okay. Mark Weiss is an expert, is a Canadian-American theoretical physicist. And he is an expert and he has done a lot of discovery of heavy quark symmetry and development of heavy quark effective theories. He was born in Canada and then got his PhD at Stanford. Supervised by Fred Gilman, if I understood correctly. And since then, he, after his PhD, wrote several highly influential papers on the p-violation in the Standard Model. He then became a junior fellow at the Harvard Society of Fellows. That was 1980 to 1983. He then went to Caltech, where he is currently a John McCone Professor of High Energy Physics. He is a Fellow of the American Physical Society, a member of the American Academy of Arts and Science, and of the National Academy of Sciences. In 2001, he shared the Sakharov Prize for Theoretical Particle Physics with Nathan Itzko and Mikhail Voloshin for the construction of heavy quark mass expansion and the discovery of the heavy quark symmetry in quantum chromodynamics, which led to a quantitative theory of the decays of C and B flavored hadrons. So let's ask Mr. Weiss to start his talk.
Okay, thank you for that kind introduction.
Please move back and forth.
Forward, backwards,
yeah,
laser. Okay, well, it's a pleasure to be here at this celebration of the Standard Model. So I was actually a postdoctoral scholar at Harvard from 1980 to 83. Shortly after the awarding of the Nobel Prize to these three young men here. And I have a lot of fond memories from my time at Harvard. One of my favorite stories to tell about that time involves, let's see if I can get it right. It involves gravitation and cosmology, Steve Weinberg, and my oldest son's circumcision. So unfortunately, I don't have the time to tell you that story now, but Steve is a very talented guy. Okay, so you'll notice that my title slide doesn't say what my talk is about. Well, if you're going to say heavy quark physics, Tetra-quarks, or the Standard Model at 50, I chose the Standard Model at 50. But indeed, my talk is about heavy quarks and Tetra-quarks. They don't seem to fit together naturally, but I'm going to talk about Tetra-quarks that contain two heavy quarks. And so you'll see that they do fit together and that there's some interesting things to say, I hope, and a future there that will tell us more. Okay, so what's the plan for my talk? I'm going to say a little bit about the Standard Model. How could I not do that? And then I want to talk about chiral symmetry, the proximate flavor symmetries of the light quarks, because the heavy quark situation is very similar to that. Then I'm going to talk about heavy quark symmetry, some of the predictions, how well they work. Next, my plan is to talk about some of the anomalies in heavy flavor physics. I'll just focus on one because maybe that's the first sign of a crack in the Standard Model. And then lastly, Tetra-quarks. If I have time left over, I have a few additional slides, but I won't. You never know, I suppose. Okay, first slide. What is the Standard Model? Everything on this slide has been said before. I'll go over it, except for the caption on the right. So what is this about? Well, if you look through PhysRev, you'll find this model, that model, supersymmetric model, technicolor model, extra dimension model. And the thing about models that's not emphasized enough, in my opinion, is that when it comes to models, in the end, there can be only one. There's only one nature as far as we know, and your model has to explain what's observed in nature. So I'm not sure which one of the gentlemen on the first slide this is. We can imagine that it's Steve Weinberg with the sword. Okay, so one of the reasons, the main reason we're celebrating the Standard Model is because it is the one. It explained the experiments that it was designed to explain. I want to discuss the Standard Model briefly from a symmetry perspective, because much of my talk is going to emphasize symmetries. And this perspective was already mentioned before in an earlier talk. And that's, if you want to say what the Standard Model is, you really don't have to write down a Lagrangian at all. You just have to say what the gauge symmetries are, SU3 cross SU2 cross the U1 of hypercharge. Then you have to give the transformation properties of the matter fields that you introduce under that gauge symmetry. So for example, you have the left-handed doublet containing up quarks and down quarks. There's an index I here because it ends up that there's 3 of these multiplets. Don't ask me why. And you have to say how they transform under Lorentz transformation. So that's a half zero under the gauge group, triplet under the SU3, doublet under the SU2, hypercharge a 6. And similarly for all the other fields or particles that are observed in nature. You'll notice that I've added here something in blue, the right-handed neutrinos. We don't know if that's right. If we don't introduce something beyond, I should say a little more. I'll come back to this later. And here's the Higgs doublet, of course. This is not, so then after you write this down, you just write down all the normalizable interactions you can write, dimension 4 or less, involving these fields. Every new operator up to some field redefinitions has a coefficient that you have to fit to data. And you have some general criteria that you have, like locality, Lorentz invariance that you also impose, and then you've got the Standard Model. You don't really have to write down the Lagrangian at all. You can deduce that Lagrangian. There's a little more you have to say, like this Higgs doublet here, the scalar doublet, it gets a vacuum expectation value. There's 2 possibilities. Either it gets a vacuum expectation value or it doesn't. If it's going to be the Standard Model where the W and Z have a mass, it has to get a vacuum expectation value. It doesn't matter where you put it. You can put it in the upper component, you can have a √2 in both components, you can always rotate it into this component, but there is that discrete choice. And so we need to say that this is the vacuum. And then, of course, we probably want a couple classical gravity, because we're fond to being stuck to the Earth. It seems like something we want to have. And so that gives you the Standard Model. If I don't add something a little more, then neutrinos are massless and it disagrees with experiment. So we have to add a little more. One option is 3 right-handed neutrinos. We don't know if that's right. Another option is a triplet, a scalar. That's called type 2 seesaw. This is often called type 1 seesaw. So I put it in blue because we don't know this is right. We know the neutrinos have mass. We know we need a little more, but we don't know what the choice is. Of course, we could also do it by adding dimension 5 operators, the lowest possible renormalizable operators. And this theory explains all particle physics measurements, as far as I know. There are a few anomalies. I'll talk about one of them later, but I don't think they've risen to the level where you would say the Standard Model is wrong. It's a pretty powerful, remarkably powerful theory. There are a few issues cosmologically. I've mentioned them here. I don't want to say more about them, really, in this talk. But there are some issues there. Okay. So I have this quote from Feynman. I have 2 reasons I want to say this quote from Feynman. One is I'm a Caltech professor, and every time I mention Feynman's name, I get a small pay increment. The other is that I really like the quote, and it applies. People have different opinions about the Standard Model. Maybe it's not elegant, it's not this, but this is really what it comes down to. It doesn't matter how beautiful your theory is, it doesn't matter how smart you are. If it doesn't agree with experiment, it's wrong. The Standard Model is not wrong. And of course, I didn't participate very much in the history of the development of the Standard Model. But towards the very end, the last sort of experimental thing that was done that put the nail in the coffin that made people sure that this was the theory was done at SLAC while I was a graduate student. I went to the seminar by Charlie Prescott explaining these results. So this was this parity violation experiment where they polarize electrons scattering off deuterium, if I remember right. And before this experiment, there were some problems with atomic parity violation, so it wasn't clear the Standard Model was right. But I remember this seminar very well. Charlie gave the seminar, and people walked out, and everybody knew this was right. It was a great thing to have as an experience as a graduate student. Okay, so quantum chromodynamics. My talk is mostly about quantum chromodynamics, properties of quantum chromodynamics, QCD, the theory of the strong interactions, and of course they'll be applied to the weak interactions as well, so I suppose it's both. And quantum chromodynamics as a subset of the Standard Model truly is, I think, one of the most beautiful theories there is. I mean, it's asymptotically free. It's defined at arbitrarily short distances. It has just a coupling constant, or through dimensional transmutation, a mass scale, and then when you add the quarks, there's the masses of the quarks, and that's it. And it explains a tremendous amount of phenomena. It has non-perturbative aspects, perturbative aspects. It's just tremendously rich and in the phenomena that it describes. So a lot of my talk is about symmetries. I mentioned how the symmetries really determine what the Standard Model is, the gauge symmetries in this case. The symmetries I want to start off talking about now are flavor symmetries, global symmetries, not gauge symmetries. And furthermore, they're not exact symmetries, they're approximate symmetries. So I'm going to start off by talking about the light quarks. So the light quarks are, for us, are the U, D, and S, and I've put them in a triplet that I've called little q. And when I call them light, I mean that their mass over some scale that characterizes the strong interactions is much less than 1. So you have to remember, this is particle physics. A half can be much less than 1, depending on how desperate you are. A third certainly is much less than 1. So we're going to treat these three light quarks as having masses much less than 1. By lambda QCD, I don't necessarily mean the parameter that occurs in the strong coupling constant. It's just some scale, say 300 MeV, to characterize non-perturbative strong interaction physics. It's not defined very precisely. A third of the proton mass would do the job. So this theory has approximate flavor symmetries, and these symmetries, they arise in a particular limit of the theory where they become exact, and that's in the limit where the quark masses go to 0. So as approximate symmetries, they'll be good as long as the masses are much less than the QCD scale. And if you set the masses to 0, the mass terms in the Lagrangian coupled left to right disappear, and the kinetic terms are invariant under an SU3 left cross SU3 right symmetry, and here I've defined it here in terms of an element L of SU3 left and R of SU3 right. And it's spontaneously broken to an unbroken SU3 vector, the SU3 vector that the multiplets of mesons and baryons fall into. What we're concerned with here is the theory of the interactions of the Goldstone bosons, the pi, the k, and the eta, associated with the 8 axial broken generators. And in this case, what you do to describe their interactions is you write down an effective field theory for their interactions at very low momenta, below this scale of QCD, let's say. And you expand that Lagrangian in derivatives, because you're interested in very low momenta. At leading order in derivatives, there's only one operator. If you go to higher order in derivatives, there's more operators with an undetermined coefficient that you would have to fit the data. So if you want to calculate a scattering cross-section, higher and higher precision in this momentum expansion requires more and more parameters that are fit to data. But usually there's more data than parameters, so it's still a valuable way to proceed. The other thing I want to say about this situation is that these approximate flavor symmetries, they arise not because the quark masses are almost equal. They're not almost equal. M up over M down is about a half. Even the SU3 vector doesn't arise because they're almost equal. It arises rather because they're small compared to the scale of the strong interactions. For the S quark mass, that's kind of dubious. We don't expect that to work that well. There'll be cases where the leading order works fairly well. There'll be cases where you have to go to high precision or maybe higher orders to make it work well. And one of the places where this perturbation theory is used is, for example, in the extraction of VUS, the element of the Kabibo-Kobayashi-Moskawa matrix, from K to pi decays or hyperon decays. And the reason you can do that is because the thing that W boson couples to, is actually the nether current associated with these symmetries. And so you can absolutely normalize it by doing the nether procedure both in the chiral Lagrangian and in full QCD. And so this is one of the methods that you use to get VUS. And here I've written 3 of the papers about 50 years ago actually, that put chiral perturbation theory into this point of view, modern point of view. It's actually the same as current algebra, which was which evolved into this. Let's just put it like that. Okay, so that's my mini review of chiral perturbation theory. And it's interesting when we talk about the heavy quark symmetries momentarily to see the similarities with this case. So I didn't know what to do with references for heavy quark symmetry, so I decided, well, I'll make everyone unhappy, except for a few maybe, and I'll cut them off pre-1991. So these are the early papers that developed this subject, or at least most of them. I want to say 1 or 2 things about a few of the names. One of them is Nathan Isker, a mentor when I was an undergraduate at University of Toronto, and a colleague who played an important role in this subject and unfortunately passed away quite young in 2001. I'd also like to mention BJ. He sort of rarely gets credit for his participation in this subject area, but he wrote a very important and influential paper. And I'm kind of sad that Howard's not here. Howard Georgi, he's usually thought of in terms of beyond the standard model physics, grand unification, meeting of the couplings, as he should be. But he's a giant in standard model physics. In perturbative QCD, the evolution of the structure functions, right after the beta function, he was on that paper, many other papers, Higgs production. Well, as I said. Okay, so enough with, so I won't mention other references unless I talk in detail about a subject area that's not covered here, and then I'll mention the particular references. Okay, so now I want to step through exactly the same words, well, not the same words, the analogous words I said about light quarks for heavy quarks. So sometimes this is called heavy quark effective theory. So first of all, now we're switching. We want to do the strong interactions of heavy quarks. Heavy quarks having masses much greater than lambda QCD. And these heavy quarks, like the light quarks, are bound in mesons or baryons that contain other degrees of freedom, the light quarks, or antiquarks, and the gluons. And inside the hadron, those light degrees of freedom have momenta of order lambda QCD, this 300 MeV. And one of the things that's important is that inside the hadron, when these light degrees of freedom collide with the heavy quark, they change the momentum of the heavy quark by an amount of order lambda QCD. But as the heavy quark mass goes to infinity, that means the velocity of the heavy quark doesn't change at all. So when you think about heavy quark physics, it's appropriate as a starting point to think of the heavy quarks as having a fixed velocity. So the heavy quark field will be labeled by a velocity label. If I have one velocity or another, a gluon collision is not going to change me from one to the other. Another thing we know very well from non-relativistic quantum mechanics, hydrogen atom, is that the physics of the light degrees of freedom, in the limit where the mass gets very large, are independent of the mass. The electron cloud in hydrogen doesn't depend on it. And they're also independent of the heavy quark's spin. So there'll be a heavy quark spin flavor symmetry. If I have two heavy quarks, there's an SU4 symmetry where I can interchange at the same velocity, where I could interchange their spin and flavor. Well, let's talk about the real world. We got three heavy quarks. We got the top, the bottom, and the charm. The charm is kind of marginal the way the strange was marginal. So there's one similarity already. The heavy quark flavor symmetry doesn't arise because the masses are almost equal. The charm is like, I don't know, 1.5 or 2, and the bottom's 5, and the top's 170. Very different masses. It arises due to this limit of the theory, so that's another similarity with the light quark case. And here comes a little point of irony. This should work best when you're dealing with the top quark, but unfortunately the top quark decays to a real W in the bottom, and that's so quick that it's not really involved in a hadronic bound state. Kind of sad if you're a heavy quark symmetry fan. Okay, here we go. So let's start to make some predictions. So this slide's kind of mathy. You can derive an effective theory in a Lagrangian, very similar to how you do it for non-relativistic physics. You redefine your field to this QV. Derivatives on QV bring down now the residual momentum because you've scaled out the large momentum. It's a two-component spinner. There's no heavy antiquark here, so it satisfies a projection like this. And then you get an effective Lagrangian with some 1/m corrections you can compute, and a leading order term that's independent of the heavy quark spin and mass, as I mentioned. So let's talk about predictions. You got some symmetries. They're usually good for making predictions. How well does it work? It involves the charm in some cases, so we have to take a look. So first of all, the mass splittings. Oh, I forgot one thing. What happens is these things occur in multiplets. For example, you have a spin of the light degrees of freedom, which you combine with the spin of the heavy quark, which is a half, and you get a half plus or minus the spin of the light degrees of freedom. So that's your doublets, unless the spin of the light degrees of freedom is 0. So these doublets, the lowest doublets in the meson sector are the B star and the B, the D star and the D. Their mass splitting comes from this term here with the 1/m. So if I look at this difference, it's the sum times the difference. The sum goes like the heavy quark mass. The difference goes like 1 over it. And so it should be constant, independent of the multiplet. So here we go. Of course, I plugged in the numbers, so the chance of these numbers being correct is not awesome, but here's what I got. So for m b star minus b squared, I got 480 in some units, and for d star minus d, 550 in some units. Not so bad, given that the charm quark is involved here. But wait, you got to be careful when you complain. I'm about to complain. When you say there's a success, because this relation, look at this, it's ridiculous. M rho squared minus m pi squared is the same. M k star minus m k squared is the same. This has a success that certainly has nothing to do with heavy quark symmetry in those cases. Maybe it has something to do with quasi-particles that make up the light hadrons. I don't think anybody really knows, but I'm certainly not prepared to call that a success of heavy quark symmetry. Otherwise, my membership to the American Physical Society will be revoked. So let's talk about something else. So the next thing I want to talk about is meson decay constant. So this could be a B meson or a D meson. These are the pseudoscalar decay constants here, FB and FD. How should this behave? Well, so this pseudoscalar meson here, so remember, nothing really depends on the heavy quark mass. There's only kinematic dependence on how things are defined. So conventional normalization of state here has a root of the mass of the state here. This is a mass times a 4 velocity, and so when you divide by that mass, you get that the decay constant should scale like 1 over the mass. 1 over the root of the mass. Square root here, mass there. And so here I've got this. And then there's another feature I didn't mention to you, and that's in addition to these 1 over m corrections, there's these logarithmic corrections that are computable, where you match the full theory of QCD onto this effective theory. In this sense, it's a little different than chiral perturbation theory, because you can do a perturbative matching onto the effective field theory. So there's these logarithms. And I actually want to mention, in the context of heavy quark theory or symmetries, a good friend of mine who passed away recently, Joe Polchinski, because one of the reasons I got started thinking about this was from a phone call from Joe where he said, "Hey, Mark," we knew each other very well. We were postdocs together at Harvard. It's kind of a strange thing. The physicists you work with when you're young, they're like your friends when you're young. They really know you. I mean, there's no airs you can put on with those members of your field. Anyways, he said, "Hey, Mark, aren't there some logarithms you can sum because the mass of the bottom quark is greater than lambda QCD when it's inside a hadron?" And this is an example of those type of logarithms that he understood must be there. So let's compare with experiment. There actually is experimental data on this, from b decays to tau and d decays, and the data is pretty good. But I'm not going to compare with it. I'm going to compare with lattice QCD. Why would I do that? Well, the lattice is more accurate right now than the experimental data, and to be honest with you, I don't have any reason to think it's not right. So why not compare with that? You might say, well, if the lattice can predict it, why are we talking about heavy quark symmetry? Well, as physicists, there's more than just numbers, right? You want to understand basic features of the numbers and certain scalings of how things would scale, and so heavy quark symmetry certainly plays a role in doing that. So here we go. Here's FB over D. FD, I put in the numbers, again, a risky business, and I got 0.7, and the real answer is about 0.9. Well, not too bad. You know, it involves 1 over m corrections. Not great, but not too bad. And I took those numbers from this review. Okay, let's go on to something a little more involved. Let's go on to semileptonic B to D form factors. And so here I've written out all the form factors here. There's lots of H plus, H minus. These are the ones that the W boson couples to, the vector and axial vector currents. This parameterization is the most general one allowed by Lorentz invariance. I've scaled out the mass dependence. When I go over to heavy quark effective theory, apart from some logarithms that are computable, each of these form factors is independent of the masses of the hadrons or heavy quarks, and just depends on the velocities. So here we go. There's a final meson with a 4 velocity v prime, an initial with v. The W boson can change the 4 velocity, even if the strong interactions can't. And these form factors just depend on W, which is the dot product of v dot v prime. It goes from 1 when they're both at rest to about 1.5 at maximum recoil. Okay, so we got 6 independent functions that are allowed by Lorentz invariance and parity invariance of the strong interactions. So it ends up, because of heavy quark symmetry, all of those form factors at leading order can be expressed in terms of one universal function that I've called Xi, and furthermore at 1 it's equal to 1. Furthermore, I mean at 0 recoil it's equal to 1. Furthermore, at 0 recoil there were no 1 over m corrections. For SU3 there's an analogous, this is usually called Luke's theorem, there's an analogous theorem called the Adam-Alligato theorem. You can do similar calculations for other state charm mesons, for baryon decays. We'll come to a moment in a few moments with how well this works. You can combine heavy quark symmetry with chiral symmetry, and you can also talk about combining it with the operator product expansion to do inclusive decays. So how well does it work? Well, again, there's data. Actually, that's sort of confusing to use the data. I have to say there's some papers that claim there's some large violations. There's other papers that claim they're not. So I'll be honest with you, I don't understand what's going on there well enough to compare with the data. Usually never go wrong by being honest, so I figure I'll adopt that policy. So what I did here is I took some lattice data on the B to D form factors, and there's probably several groups that have done this. My apologies, I just took one that made the comparison with the heavy quark effective theory for me. So remember, here's the form factor H plus that goes to 1 at 0 recoil. When you include QCD corrections, it's somewhat bigger than 1. It's not plotted over the full kinematic regime of W. It only goes up to 1.16, but it's perfectly reasonable. It's close to 1. So there's no sign of any deviations of heavy quark symmetry there. And this is this form factor H minus that was 0 to leading order in heavy quark symmetry. And you can see, at least over this range, that it's indeed small. So I think it's fair to say that, that at least involving lattice calculations of these form factors, there's no evidence for any unusually large violations of heavy quark symmetry. Okay, so that's all I want to say about heavy quark symmetry. A little touch. It's a useful thing to give you the pattern and some understanding. In the case of inclusive decays, it really is one of the high accuracy ways to get VUB, VCB, because there are no 1 over MC corrections in that case. Okay, so I want to talk a little bit about anomalies. I'm talking about heavy quark physics, and there are some anomalies in flavor physics. And I don't think it would be fair to give a talk without mentioning them. So I picked one. It's not something I've really worked on, but I'll still mention it as best I can. And it's these variables RD and RD star. So this is B goes to either a D or a D star, and it's the tau divided by, let's say, the average of the electron and the muon. So because of phase space, this should be somewhat less than 1 in the standard model. So here's the standard model prediction here. And here's the Bell and Babar. So this prediction's from theory, I should say, using heavy quark and maybe somewhat phenomenological things to predict this ratio. And a lot of uncertainties cancel out in the ratio, so I don't believe there's any reason to distrust those theory predictions. And so here's the Bell and Babar measurements and the intersection of those measurements. Here's some LHCb measurements. In the D star case, they're put off on the side not to confuse things. And you can see it's a 4 sigma discrepancy with the standard model. So that's where the situation stands now. So I want to give you a sense that things are going to get better. So I pulled this slide off of a talk. This is what LHCb can do in the future. For RD, RD star, B sub S decays they can do, RDS, D star, lambda B to lambda C decays, excited lambda Cs, B sub C to J psi. Eventually, well, this is a long time to wait. Let's go somewhere in here. We're headed for measurements of all these things with fairly small uncertainties on these ratios. Remember, these are percentage uncertainties. So I'm not an experimentalist. When I go to ask my experimental colleagues about this discrepancy, I get the universal answer back. The universal answer is taus are hard. So I think the real situation is we have to wait and see. We're going to have a lot more data. We're going to have Bell 2. This situation will get settled. With more data becomes more understanding of systematic uncertainties, and I have no doubt that this is either going to be a revolution or something that is mentioned only in history books. When is my talk supposed to end?
Whenever you like now.
Now? Okay.
No, but if you have some...
Let me say a little bit about Tetra-quarks. Yeah. Sorry. So I'll go fairly quickly through this. So if you think about quarkonium, so I want to write down, I'll pretend the quarks are different so I don't have to talk about spin labels or anything, and call them heavy quark 1, heavy quark 2. There's a there's a one-gluon exchange potential between the heavy quarks that I've calculated here for arbitrary number of colors. You'll notice it grows with NC, so in the large N limit where you absorb one NC and alpha S, it's still attractive. And the potential is minus 4/3 alpha S over R. So for heavy enough quarks, they're bound by basically a Coulomb potential. They fall into that potential. The long-range linear potential is irrelevant. So now I want to talk about tetra-quarks. And here I've written down a brilliant interpolating field that is actually 0, because this should be Q1 alpha, Q2 beta. So correct that in your mind. You'll notice that it's anti-symmetric when I make that change on the color indices of the heavy quarks. And so basically in SU3 color, the two heavy quarks are in an anti-triplet. And that's still an attractive potential. If the one-gluon exchange potential between heavy quarks and an anti-triplet is attractive, it's not as attractive as this one. It's minus 2/3 alpha S. In the large N limit, it's actually quite different. It only goes to a constant, so it actually goes to 0 in the large N limit. So perhaps that's part of the understanding of this suppression. But nonetheless, if the quarks are heavy enough, then the Bohr radius of this system, because this is attractive, when I go 1 over it, we'll have a mass scale much greater than lambda QCD. They will be deeply bound, and this will be a state that is stable with respect to the strong interactions. The B mesons it could fall apart into, or the B and B star mesons, don't have this short-range Coulomb attraction, and this will win for heavy enough quarks. So right away we know that in QCD, for heavy enough quarks, there are stable tetra-quark states in the spectrum. Okay, that's fact number 1. And so actually when I was asked to talk about tetra-quarks, I was a little bit upset. I said, well, what do I know about tetra-quarks? I haven't worked on tetra-quarks. It ends up 25 years ago, I worked on tetra-quarks. And Anish Manohar and I presented this argument. But of course, we have to confront the real world. There aren't arbitrarily heavy quarks. There's the top. Unfortunately, I told you the sad story of the top already. So we have to go to the bottom. And, you know, so if I take 1 over this Bohr radius, well, first of all, I got the 2/3, and then the reduced mass is half the quark mass. And so you end up with this over 3, and that's over only 300 MeV. So in our paper, we actually dismissed this short-range argument. But we did try to go a little further. So I want to mention one lesson with regard to this before I go on. I'm sorry I'm taking so long. But remember that there were heavy quark symmetry relations that worked for the light hadrons, the very first thing I looked at. So you should be careful about what you dismiss in this business. And I don't think we were careful enough, to be honest. Okay, but anyways, we did do something. We looked at the long-range 1-pion exchange potential. So the 1-pion exchange potential should dominate the interactions at long range. We made the short-range part just flat. We did a variational calculation, and we found that indeed there were bound states. It has to be BB star for some Fermi statistics arguments that I don't have time to go into. And it was bound by about 10 to 30 MeV in the variational argument we made, but that's some sort of lower bound. The binding energy could easily be 100 MeV. And then there's some more recent work that I think is excellent, which I've mentioned here. And they take this diquark picture seriously, and maybe you should, to be frank. And they use some heavy quark symmetry relations. One of them, for example, if I look at this difference between a diquark and a baryon containing a heavy quark, these are seen. Then in this difference, the mass at a like degrees of freedom cancels out. In this difference, it also cancels out. But on these side, we have the same difference between the heavy quark mass difference, 2 versus 1. And so this provides a mass formula. You can do 1 over m corrections to it and express the masses of the tetra-quarks in terms of masses of hadrons you know, and a few parameters. This fit was done there, and they found that there are bound tetra-quarks by a binding energy of 100 MeV. This picture does rely on this being a small bound state, but you know, maybe it works better than you'd think. And there's also important work by these authors here along the same lines, somewhat more phenomenological, but I think still good arguments. And they conclude that the binding energy could be as much as 200 MeV. So, put my cards on the table, right? You got to be a betting person. Well, you don't really have to. In fact, I guess it's considered a sin, but hey. So here we go. What do I think is going to happen? Is it going to be weakly bound by a long distance potential, sort of like a molecule picture? Or is it going to be deeply bound? I have two things to say. One, it will be bound. Two, it will be a mess. It'll be like a hadron. Not like a molecule, not really deep. It'll just be like a hadron. But I think we can look forward to the discovery of new stable states of the strong interactions. Thank you.
Where can we make the bets?
Well, I didn't take any bet. No one's going to bet against me. I was so convincing.
I don't know enough about it, but I recall a few years ago, like at the LHC, they discovered the pentaquark. Did that add anything to this entire?
So I don't think it's probably a really interesting discovery, but I don't think a similar argument holds in that case. I haven't thought about it a lot. Maybe I should think about it more, but off the hand, I don't see quite a completely analogous argument. There are 4-quark states discovered, but they're not two heavy quarks, perhaps a heavy and an anti-heavy. Those are easier to find.
Thank you again.
Good, thank you.